lesson, first we'll introduce the maximum likelihood estimation with its background and motivation. Next, we'll fix the ideas with a simple demonstration with univariate, unconditional variable, and normal distribution. Next, we'll obtain MLE estimates of a conditional variable with a two-variable regression model construct. Then we'll formulate a log likelihood function for a binomial distribution and obtain the corresponding maximum likelihood estimates. Lastly, we'll also formulate LLF for a Logit function and obtain the corresponding MLE estimates. In this video, we'll discuss the background and motivation of maximum likelihood estimation. We'll fix up the simple ideas related to distribution and setting up the likelihood function. Let us start with a simple two variable model like y equal to beta 1 plus beta 2 xi plus mu I. We are assuming that the data, that is yi, is normally distributed. So it has a mean mu and variance sigma square. So data is distributed with a mean mu and sigma square. And it has two parameters, beta 1, beta 2, this bivariate function. So every time these parameters change, the distribution changes. So this distribution is conditional to these values of beta 1, beta 2 and the value of xi. So changing with beta 1, beta 2, you will obtain a different distribution function. And we are assuming that's a normal distribution function. That means data is normally distributed. So with changing parameters, the distribution changes. Now, what we are essentially trying to do is that given these data points y1, y2, y3 and so on up till yn, these are the given data points, we are trying to infer what set of parameters, what is the set of parameters beta 1, beta 2, sigma square that would have generated this data. Now, since we have assumed a continuous probability distribution, which is normal distribution, we'll use the probability density function corresponding to this normal distribution to define the likelihood functions that we want to maximize. Please note here, the likelihood means the likelihood of probability of observing the data and joint probability because there are multiple points. So we have y1, y2, y3, y4 and so on. Assuming the normal distribution, each will have its own probability driven by that normal distribution function. We are trying to estimate that joint probability, that is the likelihood of observing the data, and later on we'll try to maximize that as well. So the likelihood is basically the joint probability of observing the data that we have. Now, assumption here is that each data point, whether it is y1, y2 and so on, they are taken from the same population. So their distribution is identical and also independent of each other. So there's no bias. So when you observe y1 or y2, y3, it doesn't affect the probability of observing other data points. And because we started with the assumption of bivariate setup where yi was a function of xi, this kind of setup. So this is a conditional probability distribution, conditional to the values of xi. So the mean of y would be conditional to the given values of xi, and it can be expressed, yi can be expressed as a normal distribution function with the mean mu given that conditional to mean mu and sigma square, when mean mu and sigma square will change with the values of xi. So it is a conditional probability distribution function. Changing with the values of xi, the probability will change. The distribution will change with changing values of xi. Now, because we have assumed normal distribution function, its probability density function is given like this. So each yi will be distributed according to this probability density function with a given mean mu and variables parameter sigma square. So you have two parameters mu and sigma square, and for each parameter you will observe the probability as this, which is conditional to these parameters. As these parameters change with the values of beta 1, beta 2, x, the probability density will also change. Now, because you are looking at n data points y1, y2 up till yn, corresponding to each x1 you have y1, corresponding to x2 you have y2 and so on, corresponding to xn you have yn. So you have n data points and you would like to maximize this probability. So before maximizing, you need to compute that joint distribution function. So what is that joint distribution function? So for example, if probability of y1 is py1, probability of y2 is py2, you are multiplying all of them to get this joint likelihood function. So to summarize, in this video, we fixed the ideas related to likelihood function. We started with the bivariate case. We had set up yi as a conditional distribution and its probability density function for each of the yi's, and we noted that from each of the individual probabilities of yi, we can multiply them to get the joint distribution, which essentially forms the overall joint likelihood function, joint probability density function, which is the multiplicative form like this. And assumption here is that each of the points y1, y2, y3 and so on are independently and identically observed. In the next video, we'll further develop these ideas to construct our log likelihood function and how to maximize it. In this video, with the help of a simple univariate unconditional model, we'll try to set up the log likelihood function and its maximization. Recall in the previous discussion, we said that for all the n values of y, let's consider them as univariate distribution. And we said that all these values are independently and identically distributed. So their joint probability function can be written like this, which is in the multiplicative form. Multiplication of each of the individual probabilities, py1, p of y into p of y2 into p of y3 and so on. This is typical joint distribution function or likelihood function. This is respect to parameter mu. Recall that parameter mu. And this is our typical likelihood function. Now, if we are trying to maximize this function with respect to the parameter mu, we are essentially trying to ask what would be that value of mu that would assign the highest probability of to the data that we observe. That means what would be the parameter mu that will result in the highest probability of data that we actually observe, which makes sense. So put this in a very simple form, you will find this expression joint probability or likelihood, and the value of mu that will maximize this joint probability will be our maximum likelihood parameter. So we are selecting the model parameters like mu or sigma square based on their ability to probabilistically explain the data. So this is our typical maximum likelihood estimation. We are trying to find those parameters mu and sigma that will maximize the probability of data that we observe. Now in practice, we maximize log likelihood because our function is a product function. We convert it into sum by taking log, particularly natural log. A very simple property of log or natural log is this: log of a into b is equal to log of a plus log of b. And also log is a univariate function. So the location of maxima and minima values are preserved. Taking log does not change these values. So if you have the likelihood function like this, you apply the log, so it typically becomes the log of this. And because now in the form of log, we can express it instead of multiplication, we can express it in the form of sums, and we can expand the multiples inside. So we'll get this minus n of log sigma, minus n by 2 log 2 pi, and minus 1 by 2 sigma square summation this. So this is our typical log likelihood function. Now we can differentiate it with respect to the parameters, that is mu and sigma, and set it 0. For example, let's start with parameter mu. So if I differentiate with respect to mu, this will be eliminated, this will be eliminated, and I'll have this function as 2 times minus 2 times inside this, and you'll get something like this: 1 by sigma square summation yn minus mu equal to 0. And here we can solve this parameter. For parameter mu, we'll get, solving this for mu, we'll get in these steps, we'll get mu equal to summation of yn upon n, which means the mean of yn itself. So the solution is the yn bar or mean yn, solving for this one. Similarly, we can differentiate with respect to sigma, del by del sigma. So this will be 1 by sigma, this will neutralize, this will be 1 by sigma cube with plus sign. So we'll get something like this. This is nothing but del by partial differential with respect to sigma, and we'll set it up to 0 to get this sigma square value, sigma, in fact sigma hat square, because it is an estimate, which is this nothing but standard deviation of yn itself. So this is standard deviation of yn. Obviously here you need the parameter mu, which you will get from here. So we have obtained both the parameters mu and sigma here in this fashion. To summarize this video, we have understood with a simple univariate setup of variable y how to convert our likelihood function into a simple log likelihood, which is easy to differentiate, and then differentiate respect to the desired parameter mu and sigma, set them equal to 0, and find the most optimum values of mu and sigma. For example, mu is this and sigma is this, which will lead us to maximum likelihood estimates for this kind of univariate setup. In the next video, we'll extend this understanding to a typical regression model in a bivariate or multivariate setting. Now that we have fixed our ideas related to maximum likelihood estimation for a univariate unconditional setup, we'll try to extend it for a regression or a simple two-variable regression model by formulating log likelihood function. Recall, in a typical two variable regression model where yi is the dependent variable as a function of xi, where yi equal to beta 1 plus beta 2 xi plus mu I. Here, the estimate of yi, which is y I had, which is also the mean of y, estimated mean, is nothing but beta 1 plus beta 2 xi, where there is no error term. This error term is not there. And the variance of variable is sigma square. So the assumption is y is normally distributed, or more specifically in this case, conditionally normal distributed. So it's a conditional distribution, conditional to xi, with the variance sigma square. Now, yi may take on many values like y1, y2, y3, and so on up till yn. So we need to understand the joint probability distribution. And this joint probability distribution with a conditional mean in the sense that this is conditional to the mean value and sigma square. So this joint distribution conditional or given the mean and variance. Also, because each yi is independent of each other. Recall we said at the beginning that these yi's are IID, independently and identically distributed. So the joint probability density function can be written as this, which can be further segregated as separately for y1 in f of y1 in conditional to mu sigma square, f of y2 in conditional to mu sigma square, and so on. So this is our typical joint probability density function, conditional to mean and variance. Also, we said that this yi is normally distributed. So its density function will also follow the normal distribution function with a given mean and variance. So recall this was the mean beta 1 plus beta 2 xi and variance sigma square. So the typical density function of fyi is a normal distribution function written like this, where this is the mean. So it's like similar to that yi minus mu mean. Now the joint distribution function, which is nothing but the multiplication of each of these y1, y2, and so on, like this, the multiplication of individual normal density functions, we can write in the multiplicative form, which is this. Now, because it is exponent, the multiplication will be converted into summation like this, I equal to 1 to n, and there's the same term which is here. So it's being multiplied n times, and because it is e to the power x1 into e to the power x2, which is equal to e to the power x1 plus x2. So you have this summative term here. Now, this is the typical likelihood function in parameters beta 1, beta 2, and sigma square. So this likelihood function is in the form of beta 1, beta 2, sigma square. Now, later on, we'll convert into log likelihood. So it will be called LLF because it will be converted into log likelihood that we discussed already. So you can see here, this is the log likelihood function. This is nothing but log function applied to this likelihood. So to this likelihood function, if we apply log to individual terms, this one, you will get this minus n log sigma. Why minus n log sigma? Because this is the power n, so you'll get minus n log sigma. Similarly, minus n by 2 log 2 pi. Why 2 pi? Because we have this 2 pi term, and then this one. So exponent will cancel and you'll get this overall this term. The square comes from this. So you'll get this overall term, which we are calling as log likelihood function. So this is the log likelihood function which you are going to maximize. And please note this log likelihood function, log has this probability of monotonicity, which means in the original function, original likelihood function, wherever the maxima minima was, that maxima minima remain the same in the log form also. So the max function which has a certain point maxima as maybe yi, the natural log of yi will be the maxima of log transformation. So this is called monotonicity, which is followed by log function, and therefore this function will attain its maximum value at the same point as likelihood function. So to summarize, in this video, we formulated our typical log likelihood function for a regression variable with conditional distribution. And now that we have formulated this log likelihood function, we would like to maximize it. Now that we have understood formulating the log likelihood function, we'll try to maximize this log likelihood function and find the likelihood estimates. Let us recall our typical likelihood function. This was our likelihood function, and we would like to differentiate it with respect to beta 1. And when we differentiate with respect to beta 1, these terms will become 0 and this will be differentiable function. Similarly with beta 2. So let's see one by one. So first we differentiate with respect to beta 1, pretty simple. We'll get this function, we'll put it equal to 0. Similarly, we differentiate with respect to beta 2. We'll get another x here because here you have xi and there was a power 2. So you'll get this one, xi equal to 0. And similarly, when you'll differentiate with respect to sigma square, you will get this typical function, which you will put equal to 0 to solve for it. So you have three equations. You'll set these equations to 0, which is the first order condition for optimization. And you'll obtain the estimates for beta 1, beta 2, and sigma square that are referred to as ML estimators. So you will set them equal to 0 first to get the estimate of beta 1, solve them for beta 1, beta 2, and similarly you will substitute beta 1, beta 2 to get a value of sigma. So solving for these, we get yi as this expression and this expression, solving for beta 1, beta 2. So you'll recall these are precisely the same expression which you got when you solve the OLS estimators. So these are precisely the same as OLS estimates, and therefore, because these are the same normal equations for OLS solution, we get the same solution as OLS. And that is why for simple linear regression, the estimates of OLS and MLE are the same. In this video, we'll try to apply our understanding of log likelihood function for a discrete probability case, that is for a binomial distribution. Think of a coin tossing game where if you toss the coin 100 times, you get n heads with a probability of p and 100 minus n tails with a probability of p minus 1 minus p. Because the probabilities are not 1 by 2, of course it is an unfair coin. But given this data that you get n heads with a probability p and 100 minus n tails with a probability 1 minus p, you can formulate the probability function, probability of getting n heads in p tosses as 100 cn, 100, this is for 100 cn combinations, p to the power n into 1 minus p to the power 100 minus n. Is this a typical expression for the probability of n heads in with the probability p? Now this likelihood changes. So if you notice, this is the probability or what we call as likelihood of getting these 100 out of these 100 tosses n heads. But this number changes as the probability p changes. We are interested in finding a particular value of p that maximizes the likelihood of getting n heads. So that p that will maximize the probability of getting n heads is the one that we desire. So let us convert this likelihood function into log likelihood. Why? Because it simplifies the procedure, and also the nature of the log function is, which is monotonicity, the maximum likelihood is same as the maximizing likelihood. We'll get the same point. So when we apply the natural log, we'll get this function, the function, original function. Recall what was the original function? This one. So this is a into b into c form. So it will be like log of a plus b plus c. How? Log of this plus, and because it was p to the power n, so n natural log p plus 100 minus n into natural log of 1 minus p. Now this function will differentiate with respect to p to find the maxima, and because of why we are doing this, because of monotonicity property allows us to do this. So we'll take the differentiation with respect to log of likelihood. So this will be 0. This will be differentiated easily, n by p. This is 100 minus n into 1 upon minus p into minus 1. So this typical expression will be this, which will be set to 0. And then we solve it in a step-by-step manner. So first step, we get this expression, and solving for this, we get p hat equal to n by 100. Now this solution, though, this is our typical maximum likelihood solution for probability p hat or estimator of p hat, which is n by 100, although it was expected because out of 100 tosses, we were finding the value where n heads are obtained. So it was bound to be n by 100, but as you can see, this is our estimates for maximum likelihood estimate of the probability for a binomial distribution. So this is the procedure through which we obtain the maximum likelihood estimate in the binomial distribution. In this video, we'll try to understand the formulation of maximum likelihood estimator for Logit models. Let us recall that the Logit model formulation under the Logit function was pi equal to 1 plus 1 upon plus e to power minus zi, where this was the expression for zi, beta 1 plus beta 2 x2i plus beta 3 x3i and so on. This was our zi, and this was our typical probability under Logit function. Here we define pi as the probability that event of interest y equal to 1. For example, if event of interest is default, so if default occurs, then y equal to 1. If default doesn't occur, then y equal to 0. So if when event occurs, interest occurs, then yi takes a value of 1, otherwise 0. And the likelihood or the probability that yi may happen, that probability pi was defined like this. Now there are two scenarios, whether the event of interest will occur, in that case y equal to 1, and 0 otherwise. So in each case, the probabilities can be simply defined for y equal to 1 as pi, which is your likelihood, and y equal to 0 as 1 minus pi, which is the probability of event or likelihood of event not happening. But also recall that 1 minus pi is nothing but 1 minus 1 upon e to the power minus zi, which is also equal to 1 plus e to the power minus zi minus 1 upon 1 plus e to the power minus zi, and this, if you multiply it by e to the power zi, it will become 1 plus e to the power zi. So 1 minus pi will become 1 upon plus e to the power zi. Now we can define likelihood function as probability that default happens, that means, or event of interest happens, which means pi to the power 1 into, if it doesn't happen, then 1 minus pi to the power 0. The other scenario would be that event doesn't happen, that means pi to the power 0 into 1 minus pi to the power 1 if opposite thing happens. So the way we can define it is 1, this pi we can substitute with this, so 1 upon 1 plus e to the power minus zi to the power yi into this 1 minus pi, which is this 1 upon 1 plus e to the power zi to the power 1 minus yi when yi doesn't take place. So overall, the likelihood can be written as very simply this function into this function. So suppose if yi equal to 1, this is equal to 0. So this is p, so p to the power 1 into 1 minus p to the power 0, which is effectively nothing but pi itself, or the likelihood function. So this becomes our typical likelihood function that we can maximize. So let's further look at this joint likelihood function. And now, because there are n observations for I equal to 1, 2, and so on, you'll have a typical likelihood function L theta for variables x2i, x3i, so on for xk. What are these x2, x3, and so on? These are these values under the z function. Now, for this function, for each values of I equal to 1, 2, 3, and so on, you will get multiple values and parameters beta 1, beta 2, beta 3, and so on. Because this is in multiplicative form, you will get this function. Multiplicative or product of I equal to 1 to n, this one, pi to the power yi into 1 minus pi to the power 1 minus yi. Now, because we are taking it, converting into log, natural logarithm, converting into log likelihood function, this will be now summation of I equal to 1 to n yi into natural log of 1 plus e to the power minus zi plus 1 minus yi natural log of 1 plus e to the power zi. So why this summative form? This summative form is achieved because it is a logarithm. Now all you need to do is you maximize this kind of function, you maximize this function, and you get your log likelihood functions maxima. So maximizing this function will give you the log likelihood function maxima that you want. So in this video, we summarized how to obtain the maximize the likelihood function for a Logit class of model. To summarize this lesson, maximum likelihood offers an extremely powerful approach to nonlinear models where OLS is not very useful. In the linear models also, maximum likelihood approach provides the same estimates as ordinary least square estimates. MLE approach finds those parameters that maximize the joint probability of the observed data. MLE is asymptotically unbiased and provides minimum variance, that is, as the data grows, it becomes unbiased and efficient, and therefore is a consistent estimate. Likelihood values also offer goodness of fit of a model and can be used in applications such as testing the overall fit of the model, similar to F-test in OLS, pseudo R-square, and computing information criteria. MLE is more general than OLS and is employed for a wide range of model applications.